All right, let's go back to applications. We did free fall without air resistance a week and a half or so ago. Let's now do free fall with air resistance. Once again, I'll take the opportunity to talk about vectors. Vectors are going to be a bigger deal for us next week when we talk about systems of differential equations and generalizing the slope field to something called a vector field. We'll introduce that idea. So I've got a ball here, a mass, M, under the influence of gravity. That's certainly one force on the mass, F vector sub grav. I make my vectors with little half arrows like that. In books, they're often bold-faced instead. If I decide to define I hat to be the unit vector that points directly to the right, and J hat to be the unit vector that points directly upward, then I can say the force due to gravity, because it points straight downward, is a negative multiple of J hat. In fact, the magnitude of that is M times G. Because it's in the opposite direction as J hat, I'd write it as negative mg J hat. That negative sign means it points downward. There's also a force due to air resistance. We are now trying to model air resistance. Should make some intuitive sense that air resistance points in the opposite direction as the velocity vector. The velocity vector points straight upward when the ball is moving upward. So the air resistance would point downward. And when the ball is moving downward, the air resistance is going to point upward. It's always in the opposite direction as the velocity vector. Let's pretend the velocity vector is pointing downward at this moment in time. This red arrow, let's pretend that's the velocity vector. V with a little vector symbol above it. There's a couple different ways this velocity vector could be represented. One way to represent it is as the derivative of the height with respect to time times J hat, where Y is the height as a scalar quantity. Positive when you're above the ground, negative if you were below ground, like if there was a hole in the ground and the ball fell into the hole. Its derivative, dy dt, could be positive or negative. It'll be positive if the ball is moving upward and negative if the ball is moving downward. And 0 at the instant when the ball reaches the peak, if it's going up before coming down. At the moment where it's at the highest point, the instantaneous rate of change of the height with respect to time is 0. The graph of the height with respect to time is going to be concave down. Wherever that tangent line is horizontal, that's where dy dt is 0. For the sake of convenience, I will also write this as cursive v times j hat. Careful here. I'm not thinking of cursive v as the magnitude of the velocity vector. The magnitude or length of a vector always has to be greater than or equal to 0, never negative. But I'm allowing this v to be negative. In fact, it's going to be negative when the object is falling. By the way, yes, this is called free fall even when the object is moving upward, because it's still being affected by gravity and it will eventually come back down, as long as it doesn't reach escape velocity from the Earth's surface. Can I clarify that? V here is not the length of the velocity vector. It's the rate of change of height with respect to time. It could be positive or negative. It's a little inconsistent with notation commonly used in physics. But if v is negative like this, if the velocity vector is pointing downward, then the force due to air resistance, the drag force as it's sometimes called, will be pointing upward. F sub air, I'll call it. Could call it F sub drag. Points upward if v points downward. What is its formula? That's not so clear. In fact, the formula for the air resistance in terms of the velocity vector could be different for different objects. A rock versus a feather, for example. Make sense? It could be a different formula, a different kind of formula even. We're going to do the simplest possible model. We're going to assume that the magnitude of the air resistance force is proportional to the length of the velocity vector. Magnitude, length, size of a vector, those all mean the same thing. How long is the vector equals the magnitude of the vector. In most science books, they don't bother doing what I'm about to do, but you will see this in a lot of math books. Some math books put absolute value signs around the vector to indicate its magnitude. Other math books put double absolute value signs around it. I actually prefer the double absolute value signs. The point of the double absolute value signs is that it emphasizes that you're taking the length of a vector as opposed to the absolute value of a number. They're related but distinct concepts. This can't be negative. I'm going to assume it's proportional to effectively the speed. So what I'm writing down doesn't take the direction into account. Some constant of proportionality, k, where k is positive, times the speed. What is the speed? The speed is the magnitude of the velocity vector. That's a velocity vector there, which you could also say is the absolute value of the rate of change of the height with respect to time. Absolute value of cursive v. This is a vector v. Cursive v is not really the vector. It's the rate of change of the height with respect to time. Could be positive or it could be negative. Its absolute value as a number is the same as the length of the velocity vector. By definition. Nothing beyond a definition going on. What does that mean about the air resistance force itself? What form does the air resistance itself take? Here we want to take the direction into account. Upward when the motion is downward, in other words, when cursive v is negative, and downward if the mass was moving upward, if cursive v was positive. Cursive v is the rate of change of height with respect to time. The height is decreasing with respect to time when the object moves downward. So cursive v would be negative. If it's moving up, then the height is increasing with respect to time. Cursive v dy dt would be positive. So it turns out this ends up equaling negative k times the velocity vector. In order for this condition up here to hold, and for the to point in the opposite direction is the velocity vector, that's got to be its equation. Make sense? Am I going to test you on a derivation like this? No. But I think it's worthwhile to go over in class because taking math and physics classes beyond this, it'll be helpful for you. These kinds of derivations of equations of motion arise in all sorts of physics classes like mechanics, for example. In mechanics, you do this kind of thing every single day in different situations. Mechanics is not about the mechanics of like repairing a car. It's about motion. So what do I do with all this? Remember, our topic is differential equation. Differential equations. Where's the differential equation? You always need Newton's second law. Newton's second law can be written as F vector equals m times a vector. F is the total force, sum of all the forces acting. In this case, it's F grav plus F air. A is the acceleration vector. That is the rate of change of the velocity vector. You could also say it's the rate of change, the second derivative of the position vector, which effectively is the height times j hat. The position vector, if you take the ground level to be position 0, the object's above ground for all of our practical applications, and so it would be the height times j hat if we're always above ground. Let's just leave it like this then. F, again, yes, needs to get replaced by the sum of all the forces. In this case, there's two forces. The gravitational force, as we see up here, equals negative mg times j hat. What about the air resistance force? Well, it equals this. That can be written in terms of j hat. That's what I'm going to do now. Write this air resistance force in terms of j hat. If you're careful in thinking about this, you end up realizing it's k times cursive v times j hat. Why? Well, first of all, the length is right. J hat has unit length. The absolute value of negative k times v is positive k times v. That would be the same as the length of this vector, positive k times the magnitude of v. And it's got the right direction. If the vector v, the velocity vector, is pointing upward, so the motion is upward, that means the scalar cursive v is positive. K is positive, so this is a negative constant in front of j hat. The air resistance vector points downward. On the other hand, if the object is falling so that the vector v, the velocity vector, points downward, that means cursive v is negative. Negative times a negative is positive. This quantity points straight upward. Negative k is going to be a negative constant, times cursive v is negative when the object's falling. Negative times negative is positive. This is a positive multiple of j hat. It points upward. You might feel like, yeah, I get that. But then realize if you thought about it an hour from now, you might forget what I said. It's worthwhile to think about again, to not just completely forget this, even though I'm not going to test you on this kind of derivation. So put that down here. This is negative kv times j hat. Then you can factor out the negative. You can factor out the negative sign as well as the j hat. Let me just not factor out the negative sign. Let's factor out just the j hat. I should write this in terms of j hat as well. There's the vector v in terms of j hat. Just differentiate both sides, which means differentiate that thing. The rate of change of cursive v with respect to t times j hat. Effectively, if you're confused by looking at this, effectively the rate of change of the velocity vector equals this, the rate of change of the scalar velocity times j hat. A scalar velocity cursive v, which is defined to be the rate of change of the height with respect to time. It's not easy, okay? The differential equation is to set these two things equal to each other. Feels tempting to say, cancel the j hat, make it go away. Is that valid? It turns out it is valid, but not because you're dividing both sides by j hat. You can't divide by a vector. But if your vector is a multiple of j hat, whatever the coefficient is, if these two things are going to be equal, the coefficients have to be equal. So our differential equation, our first order diffeq as a scalar quantity is the rate of change, or m times the rate of change of cursive v with respect to t equals negative mg minus k times cursive v. Looking right there and just getting rid of the j hats. It is okay to do. I'm equating components, you might say. More commonly, you would divide both sides by m and write this as the rate of change of cursive v with respect to time equals, here the m's cancel, negative g minus k over m times v. And this is a right-hand side function, just of v, no t's. This is an autonomous differential equation. Diffeq. Let's solve it. Might be nice to use particular numbers. We'll use standard numbers, 9.8 meters per second squared for g. K and m, let's just take to be simple, 1. M would be in kilograms. K technically would be, if you're interested, in units of force per unit of velocity. Newtons per meter per second. It's not a big deal. I'm not going to test you on that. If I use these things, then the equation becomes this. This is autonomous and it is separable. Divide both. Well, let me factor out a negative sign here first. Divide both sides by 9.8 plus v. Pretend to multiply both sides by dt. I'd get dv over 9.8 plus v equals negative dt, which I should probably write as negative 1 dt. And then integrate both sides. This integrates to negative t plus a constant, called the constant c1. This integrates to natural log of the absolute value of 9.8 plus v. Which our goal is to solve for v, so try to get rid of the logarithm first by exponentiation. Let me do 2 steps at once. Let me exponentiate there and also get rid of the absolute value signs. That does end up being okay to do, though I'm not fully justifying it. E to the c1, you might call c2. If I get rid of the absolute value signs, you might call it c3 or just maybe a plain c. Finally, subtract 9.8 from both sides. The velocity as a function of time is some constant times e to the negative t minus 9.8. There's your general solution for the scalar velocity. Use it to solve an initial value problem. Say v naught is the initial scalar velocity. Replace t with 0. C e to the negative 0 minus 9.8. That's 1. So this is c minus 9.8. Add 9.8 to both sides. C is 9.8 plus v naught. And therefore, the unique solution of the IVP consisting of this differential equation and this initial condition is this function, replace C with 9.8 plus V naught. V equals, in parentheses, 9.8 plus V naught times e to the negative t minus 9.8. What would the graphs of such solutions look like? Make a TV plane. One special solution is when V naught is negative 9.8. If V naught is negative 9.8, if you throw the ball downward initially with a downward velocity of 9.8 meters per second, that'll be zero. It'll go away. And your function will always equal negative 9.8. Negative 9.8 generates an equilibrium solution. Equilibrium solution. Pretend that's a horizontal line. What about other solutions? If V naught is bigger than negative 9.8, whether positive or maybe like negative 5 or something, that quantity right there in front of the e to the negative t is positive. Got a positive exponential decay, then shifted downward by negative 9.8 units. The graphs for various initial velocities look like this. Exponential decay toward this equilibrium solution. And if the initial velocity is in the downward direction and bigger than 9.8 in magnitude, then this coefficient right here is going to be negative. Graphs of some negative number times e to the negative t go up. They're going to look like this. Because these solutions approach the equilibrium solution as t gets larger, we give a special name to the equilibrium. We call it a stable equilibrium solution, because the nearby solutions approach it as t goes to infinity. Question?
How is the equation we found relates to the vectors we're doing?
We use the vectors to derive the equation. So we were thinking about the vector diagram in order to see that these things have to be equal. And once we got those things equal to each other, since they only both involve j hat, we could get rid of the j hat and just get a scalar equation. If your motion is not one-dimensional, if it's like two-dimensional motion, then you have to think about the vector equations more carefully. You might have both I hat and j hat involved. It gets trickier. So it's worthwhile to think about the vectors first. But here it simplifies, and in the end, you really don't have to. What about the height, though? Wouldn't we want to know the height? The scalar velocity is the same as the rate of change of the height. By definition, that's a definition. So the equality between dy dt and this thing on the right-hand side is another differential equation for the height. Integrate once to get the velocity, integrate again to get the height. And in fact, it's a pure antiderivative problem. It's not autonomous. There's no y on the right side, only t. A plain old regular integration is good enough to solve that. Y is going to be the integral of, in parentheses, 9.8 plus v naught times e to the negative t minus 9.8. Integrate that with respect to time. Looks harder than it is. It's a fairly easy integral to do. There's how it would turn out. Use the initial height to figure out C. This is a 1. This all simplifies to C minus 9.8 plus V naught, or excuse me, minus V naught. Solve for C by just adding 9.8 to both sides and adding V naught to both sides. C is going to be 9.8 plus, don't forget the Y naught here, Y naught plus V naught. So the height, Y, in terms of both the initial height Y naught and the initial velocity V naught, look right here and replace C with this. I'm using parentheses over here. I don't have to use parentheses. That'll be the height as a function of time. What does its graph look like? With this code, I'm going to plot it as a function of t for different values of Y naught and V naught, is effectively what this is doing. Do you need to know this code for the exam? No. T is horizontal, Y is vertical. Ignore when Y goes negative, because that would be going underground. For Y naught being 0 and V naught being positive 10, the motion is described by this graph right here. That's not meaning the motion is two-dimensional. Motion is still up, down. The horizontal axis here is time. If I increase the initial velocity, as you would expect, it stays in the air longer. Here the graph kind of looks like a parabola. Here it definitely does not look like a parabola. Actually, in both cases, they're not parabolas. You could see the graph is getting close to being straight over here. That should make sense. The velocity is approaching a negative constant, negative 9.8. That's the same as the approximate slope of this part of the graph. This part is close to negative 9.8 in slope. Since the velocity is approaching a constant negative 9.8, my guess is this certainly works a lot better as a model for a feather than for a rock. But there are other complications to take into account with feathers, for example, is you could have an updraft and the feather could move up. You know, it also sort of tends to float around like this. So it's kind of more complicated for a feather than this is indicating.